Hi everyone, Dave back again, continuing on with looking at the shapes of molecules. I'm actually going to start by reminding you of what I've already told you in that previous part of the lecture. Whoa, if I go the right way, sorry about that. Okay, if you recall, I said the idea behind this was that you assume that electrons in bonds tend to repel one another, and they try to maximize the distance between them. And I talked about, for example, methane looking like this, and the reason being is that you have, oh sorry, I did it again. The reason being that for carbon, you've got an electron there, 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 and there, if I draw Lewis dots, and then it binds covalently with hydrogen, like that. Okay, I'd never be an artist, like that. And then these electron clouds try to repel one another. And for carbon, because we can work in 3 dimensions here to maximize the repulsion, you end up with this thing called a tetrahedral. It's a tetrahedral shape, and there's a bond angle between these bonds here of 109 degrees. I then went on to nitrogen and showed you that's the shape of nitrogen there, and if you look at the Lewis dot structure, we've actually got one pair of electrons that aren't involved in bonding at all. And if we look at it with hydrogen, it's going to look something like that. Okay, so we've still got, if you like, 4 sets of orbitals here that want to repel one another, which is what's going on here. There's one bonding set, another bonding set, another bonding set, and there's our non-bonding set. But so it still forms a trigonal coplanar structure, at least in the first instance. You can think of it that way. But then because these electrons here are actually more concentrated, they push harder in this direction and actually squash this bond angle here from 109 to about 107 degrees. And we change our naming system. We no longer call it a tetrahedral shape, we actually call it a pyramidal shape. I got up to here, this is oxygen. So what's going on with oxygen? Well, if we look at the Lewis dot structure for oxygen, it's actually got 2 pairs of non-bonding electrons. So I've got a pair there, say, and a pair there. And it's only this electron here, whoops, should write that as a dot, this electron here and this electron here that are involved in bonding. So that can form a bond with hydrogen, and that can form a bond with hydrogen. So I've still got this 4 cluster of electrons going on, like this. So in that sense it's no different to methane with that tetrahedral shape. But in this case, I've now got 2 lots of non-bonding electrons pushing even harder down in this direction here. And they're pushing against each other pretty hard this way as well. So the bottom line is, this bond angle here, which you could originally think of as being 109, actually shrinks from 109 to 107 that you'd expect with ammonia, down to about 105 degrees. So if you look at or think about the structure of oxygen compounds, they're kind of like boomerangs, like this. Like that. And there's our bond angle there of 105. Now in this case, here, I didn't write in these non-bonding pairs. I'll do it right now. And now you can see what's going on here. Squash, squash. That's just another way of representing it. My diagram's far more amusing. Okay, so that's oxygen. remember I said that it's not only oxygen, but all elements that sit under oxygen in the periodic table. So we've actually covered pretty much all of the non-metals and the formation of covalent compounds, and indeed the sorts of structures and shapes that you would expect. Now, at this point, none of it makes complete sense to you because I don't think you can see the practical connection between what I've shown you and how you can explain various physical phenomena, but that's going to occur in the next lecture or two. Just for completeness, if we look at fluorine, which is obviously in the halogens, they're all linear molecules, right? Because you've got this structure here. You could regard it as tetrahedral if you wish. So this would be fluorine here. And if I put this as a hydrogen here, sure, these things can squash one another like this, but the bottom line is this is a straight line between the hydrogen and fluorine, so obviously all of these types of molecules are linear. Alright, there's a little summary for you. I hope you've enjoyed the lecture. The next one will make things much more complete.